Welcome to the Kentucky Watershed Academy. I'm Steve Evans with the Kentucky Water Resources Research Institute. And in this section of Module 2, Water Quality Basics, we're going to be learning more about geomorphology. At this time, we refer back to our stream functions per pyramid, which we looked at in the overview. We've already covered the hydrology and hydraulics in a previous session. So in this session, we're going to look at the third component, geomorphology, and specifically fluvial geomorphology. Geomorphology refers to the study of landforms on the Earth and the processes that change them over time. Fluvial geomorphology refers to the structure and dynamics of the stream and river corridors. These concepts are especially important to understanding the formation and alteration of the stream or river channel, as well as the floodplain and associated upland transitional zone. In terms of stream function, the functional pyramid restricts the idea to the transport of wood and sediment to create diverse bed forms and dynamic equilibrium. The hydrology and hydraulic functions come together with the geomorphology functions to create a channel form that is appropriate for the underlying geology and climate of the region. So when we discuss geomorphology, we're going to be looking at sediment and debris transport and deposition, erosion, channel evolution, bank stability, riparian zone, bed material, and form. In order to understand fluvial geomorphology, let's break it down into its component parts. Fluvial refers to the processes associated with running waters. Geo refers to the earth, that is the sediment and the rock, and morphology refers to the study of the channel shape. So you have water, earth, and then a shape study. So fluvial geomorphology is the study of the form and function of streams and the interactions between streams and the landscapes around them. It seeks to explain why streams and rivers look the way that they do and how they change over time. There's an ancient Greek saying, "No man ever steps in the same river twice. It's not the same river, and he is not the same man." We want to begin this session by noting that streams are never the same. Every time you enter a stream, there is new water flowing in it. The sediment and the rocks are different. There is a different vegetation that is either grown or left. The root system is different. The organisms in the stream are different. It is a living ecosystem, and even though it looks like the same stream, it is not. Dynamic equilibrium is a key concept for understanding fluvial geomorphology. The idea is best illustrated by a balance. If something happens to one side, the other side will adjust to try to find a new balance. In fluvial geomorphology, the balance has water on the one side and earth or sediment, that's rocks, the geo portion, on the other. The shape of the stream will change to adjust to changes on the other side. Streams are always changing, both the water in the stream and the sediment and the rocks over which the water flows. There's a natural equilibrium. But rapid changes in the environment can alter the balance and cause streams to change more quickly and with potentially damaging repercussions to human property and stream ecosystems. As we've already drawn attention to in the hydrology and hydraulics section, there are different zones of the stream, and these different zones work differently with erosional processes. In the headwaters, you tend to have much faster flowing streams that are transitioning energy and causing more erosion. You have both erosion and sedimentation that are occurring in that transfer zone. And then in the depositional zone, there tends to be more area there where things can slow down and settle out. So recognizing that streams change, what does a balanced or a stable stream look like? The EPA has put forth two statements here that I think help to give us an idea. The first says, streambed is not grading or degrading over time, and lateral adjustments do not change the cross-sectional area, even though its position in the landscape may change. So that means that there's a balance between the sediment that's coming in and the sediment that's going out, even though it may move across the landscape. The second statement says, sediment particles that erode and are transported downstream from one area are replaced by particles of the same size and shape that have originated upstream. So again, there's an idea of movement, but of replacement. This idea of a balance or a dynamic equilibrium is best illustrated through what's known as Lane's alluvial channel equilibrium, also known as Lane's balance. It is a basic fundamental concept for understanding fluvial geomorphology. It involves the interplay of four basic items. On the left side, we see items related to sediment and on the right related to water. So on the left side, we draw your attention to first the sediment load times the sediment particle size, and that will be proportional to the stream of flow times the stream slope. When all four factors are in balance, the stream is in dynamic equilibrium. So think about a mild rocking back and forth that you would see here. As one adjusts, the other adjusts, and they kind of come in balance with each other. However, when one of the factors changes rapidly, the stream will begin to degrade or aggrade to a new equilibrium. For example, if a stream discharge increases, more water is coming into the stream, the scales will tip towards degradation. That is, begin to dig down and erode the stream. Let's take another example. If an erosive activity is occurring in the stream headwaters and delivering more sediment to the stream, the scales will begin to tip towards aggradation. That's because the stream was in balance and now there's more sediment that's available and it no longer has the capacity to carry all that bed load down the stream. So it is deposited in the stream itself. So how does the stream begin to correct for this imbalance? Well, perhaps the sediment load begins to cut off of a stream meander, and so the stream can straighten the stream channel, and so it can generate greater flows that can move more easily through the sediment load. This would be like a stream cutoff or an oxbow lake. Now we're going to imagine a scenario where you have an overgrazed watershed. So that's causing a lot more compaction of the soils that is occurring, and so that will lead to increased stormwater runoff and therefore increased stream flows. Well, how is the stream going to address this issue because it has now more water that's present there? Well, the scales will begin to tip towards the right and degradation or erosion of the stream will occur. So how does the stream correcting? Well, as that erosion is occurring, the stream is digging down. So that's going to lower the slope and begin to start to correct some of that balance. And as that erosion also occurs, it will be depositing the particles from the banks, moving it from downstream, and it initially will straighten, but then it will begin to wiggle back and forth, creating meanders for itself. Let's take a look at how this could work. Here we have a time-lapse simulation of what it looks like in sandy soil when water is pulsed through a straightened stream. As you can see, the channel shape begins to meander and to seek a shape that better conforms to the sediment size and shape over time. The stream is adjusting to reach equilibrium by changing its shape. Here we see another example of the process of erosion occurring. So erosion is happening as the flow hits the side of the river flowing downstream. You can kind of see as those particles are moving it, they're spiraling throughout as they bounce across the banks. So the stream shape is changing through that erosion and sediment transport to adjust to the changing discharges of the water. So as the water is spiraling downstream, the fastest waters cause erosion on the outside of the stream bends. But the slower waters are on the inside of the bank, and that's where deposition is occurring. So over time, erosion occurs on the outside, deposition on the inside, and the stream will begin to increase its meanders across the floodplain. Here we can see in this unanimated diagram a cross-sectional view that shows how the channel meanders. As we saw in the previous clip, the water in the stream moves in a helicoidal flow. That is, it's moving forward in a spiraling fashion. It moves from the top outside to the bottom inside across the meander as it moves downstream. You can see that in the circled area. This transports sediment eroded from the concave bank downstream to the next convex bank. On the inside of the channel, the point bar expands as sediments settle out due to the slower flows. On the outside, the fastest currents cause erosion and can undermine the bank. The greater erosion on the concave bank occurs just downstream of the axis of the meander bend. This causes the meanders to migrate down the valley. The lateral erosion of the meanders and their migration widen the floodplain, and thus the asymmetrical pattern reinforces itself. Here is the same example from another view. The width of the channel remains relatively constant, while the whole channel migrates laterally and becomes more sinuous. Sinuosity is described as the actual channel length divided by the straight line distance. If sinuosity becomes too great, the river in a flood may be able to break through the meander neck, thereby straightening its channel. The abandoned channel, a cutoff, may be used during a flood, but frequently the ends of the nearest course become blocked with sediment and the channel becomes a small lake or an oxbow lake. This time-lapse video gives us a better understanding of what is occurring. So here we can see the lateral movement downstream of these meanders, and you can begin to see one of those meanders is coming close at the very bottom of the stream of pinching off and forming one of those oxbow lakes. You can also see other watercourses where it's moved across the floodplain over time. This is dynamic equilibrium at work. Disturbances in the landscape can cause the regular balance to be thrown off, resulting in rapid catastrophic changes, as well as long-term unstable conditions as the stream seeks to slowly regain some of that dynamic equilibrium through its slower processes. In response to disturbance, the stream channel will move in one of four ways. It can move up through aggradation, that is, the stream elevation increases due to deposition of bed sediment. It may move down, that is, the stream elevation decreases due to erosion of the bed sediment and incision. It can move in, the banks may narrow and the stream width decrease due to bank building by slumping or toe benches or berms. Or it can move out, the stream width increases through bank material removal through erosion, failure, or toe scouring. So you can see on the right side, you have a building up of the stream through aggradation or narrowing. So you may have formation of a point bar or a side bar or an island or a delta. Whereas on the left side, you can see through widening or degradation, this may be a head cut or channelization disconnected from the floodplain or increased entrenchment. A head cut can form with a sudden downcutting of the stream bottom to adjust the slope or the elevation. This is when the stream surface is lower than the surrounding valley floor, with the stream being confined between steep banks. So this kind of looks like a miniature waterfall, and a head cut will slowly migrate upstream as it becomes deeper as it progresses. So when you see multiple head cuts in these migrating streams, it may be a sign of past channelization and increased stream slope, causing the stream bed to degrade. As the bed elevation decreases, the stream channel becomes more deeply incised with steeper banks. When we talk about disturbance of the stream, what do we mean by that? Well, these are things that adjust either that water side of the balance or the sediment side of the balance. Okay, so some common disturbances may be a dam or a water withdrawal. It may be a channelization or a straightening of the stream. It may be changing the land use in the area. It may be irrigation, soil compaction. Perhaps it's dredging, removing some of the volume, the sediment from the stream, or gravel mining. It may be a channel crossing, either for a vehicle or for animals. It could also be timber harvesting or even urbanization. Okay, let's look at some different scenarios to understand how this balance works. So let's say the volume of water entering a stream changes due to a dam or reservoir construction, or perhaps it's a withdrawal upstream, or it could just be drought conditions that are occurring as a result of climate change. The point is, because the volume has changed, the stream no longer has the force to move the same size sediments and debris that it once did, and therefore sediments will begin to settle out or aggrade. Only a portion of the channel previously used will be utilized. So over time, there will be adjustment, and the the stream will operate into a much smaller portion of the floodplain of the system. Let's take a different example in which the disturbance adds more sediment. So perhaps this is through a logging operations that operates without a master logger and according to the standards there. Or maybe it's a home construction site that contributes a lot more sediment and dirt and doesn't use proper erosion controls. So this addition of sediment to the stream, that stream does not have the slope or the discharge capacity to pick up all the particles and transport them. The sediment will deposit and there's nothing else that can pick that up, so it's going to raise the level of the stream. The stream will move slowly in order to form and create a new channel over this surface. Let's say a lot of development occurs in an area, causing more runoff to enter in the stream. In that case, the additional water discharge will start eroding, degrading the stream because now it has the force to move particles that it didn't before. Let's try a different mechanism of disturbance, increased sediment transport. So in this example, say there's regular ATV use in crossing the stream or even moving along the stream. What's going to happen? Well, this use will dislodge sediments from the stream banks and bottom, and it'll be transported into the water column. The sediment is not normally eroded by the stream, and therefore deposits downstream, changing the shape of the stream. The stream will be unstable as it seeks to establish a new channel shape. Or let's say that some large boulders, big enough that the stream cannot move them, are added to a stream that is unstable due to increased flow rates. These boulders can help stabilize the stream if they're added at a riffle or even at a bank, because these cannot be moved by the water. This is an example of a stream restoration technique called a crossvein, which helps to slow the water velocity and creates eddies where the water can help to cleanse itself. Here's an example of another type of restoration activity. This is one of Kentucky's stream mitigation projects in Knott County. So note the sharp bends on the stream with the severe erosion on the left, which would be continuing to contribute towards significant sediment loading to the stream. Following restoration, the banks have a more gradual slope, allowing for flows to spread out over the floodplain and reducing erosional pressures on the bends in the stream. So stream restoration is helping to speed along this process of adjustment and quickly allow the stream to come to a more stable environment that may take hundreds of years if it was to do it on its own. Having given an overview of some of the principles of fluvial geomorphology, we now want to look in turn at 5 different measurements of the forms and functions of fluvial geomorphology. We're going to step through sediment, debris, and transport, bed material, bank erosion and stability, channel evolution, and riparian vegetation in order to understand some of the ways in which hydrologists will measure how well each of these functions is performing in a stream. An example of this might be something like a pebble count analysis, which is going to measure the pebble size and numbers to account for the bed material as well as the sediment transport. So we want to begin with stream flow and sediment transport. We know that sedimentation is a major pollutant, and so it's helpful to think through how sediment is transported in a stream. There are 3 different ways in which sediment is transported. One is bed load, that sediment that rolls, slides, or bounces along the bottom. You can see that in the picture to the left. Second is suspended load. You can see that in the picture in the middle. It's the amount of sediment being carried downstream by flowing or moving water. And the third is the wash load. You can see that in the picture on the right. This is the portion of the suspended load that will not settle to the bottom during low flow. When you measure the total suspended solids in a stream, you're only capturing the suspended and wash loads. Large boulders and cobbles will move, but typically not very far. When we talk about sediment transportation, we're essentially talking about 2 things. How big is the particle, and how fast is the water moving? In this diagram, it helps us to understand the relationships between when particles can erode from the bank, when particles may be transported from the water, and when particles may be deposited. You see three different colors in our chart. The first is the particle erosion. And so this area is telling us when particles may be eroded from the banks. The gray area is the area in which particles may transport. And lastly, you see in that brown area is when sediment will be deposited. You can see along the bottom that there's different sizes. At the top, it gives the millimeter of the size, and then it gives a characterization of clay, silt, sand, gravel, or pebbles, cobbles, and boulders. And then on the y-axis, we see here the flow from slow to very fast at the top of the chart. So let's try a couple of examples here. Okay, so first I want you to pay attention that is looking at the speed of the water on that y-axis, not the amount of the water. So you can take the same amount of water and put it in a small area that is concentrated. And is that going to increase the speed or decrease it? Well, if you answered increase, you're correct. So this is what happens when a stream cannot extend out onto its floodplain. Its speed and its power increases. When it can spread out onto its floodplain, it slows down. And so when that stream is concentrated, that's why we say its erosive force is going to increase. Similarly, the meanders will help the bank to slow down. So again, let's look at some examples. We're going to pick on the left side a velocity of 100 centimeters, and we're going to follow it from the left side of the screen to the right. So first we can see that this speed is able to transport clay, but it is not able to erode it because clay particles hold tightly onto the banks. If we continue to move across, we can see that it will erode silt and sand and even some gravels. And at the gravel, we can see that it begins not to be able to erode at the higher end of the gravels, around 10 millimeters, but it will transport it. But then it will not be able to transport pebbles, cobbles, or boulders. What about if water is flowing slower, maybe at 1 centimeter per second? So we're going to follow across that 1 centimeter there. Okay. Well, what would erode from the banks? Well, that type of flow will not erode anything from those banks. What will it transport? Well, it may move along. It has enough force to move along clay or silt, but sand, gravel, or pebbles, cobbles, boulders, that's going to settle right out. Okay. So what is a stream bed going to look like at the top of the hill where there's a lot of velocity and slope? It's going to have more pebbles, cobbles, and boulders because those can't be transported. What will the stream bed look like at the bottom of the hill where there's a lot of velocity and slope? Well, it's going to have more sand, silt, and gravel that settles out from upstream. And so this can help us to see when something can be removed from the bank, when it can be transported, and when it's going to settle out. All right, next we want to turn to our look at the bed material. And so in order to determine the size of the particles in a stream, a Woolman pebble count may be conducted in which a person walks back and forth across the stream and measures the first pebble they touch without looking. And they do that 100 times. And then they can take a gravelometer or a ruler to measure the size. So they try to take that rock and they see which one of those different holes to that gravelometer in the top right it can fit through. And they record the size of that rock. And this can be plotted after they've gotten all of those different rocks together. They plot it and you can determine the medium particle size and other information. Alternatively, individuals can just estimate the amount of each type of particle: clay, silt, sand, gravel, cobble, boulder, bedrock, within the riffles, runs, and the pool, and what percentage of these represent. This information can help determine what the size of the sediment will be transported under different types of flow conditions. So we go back to that previous chart, and we can see, well, if the flow is this level, it's going to cause this to erode off. And you can see what is being transported. So now we turn to this bank erosion and stability function. So every watershed plan will need to have some sort of quantification of the erosion in the watershed. A range of approaches can be used to quantify erosion. At the very simplest level, just recording the locations and lengths of the stream with severe erosion, they could just identify that visually using the Maryland Stream Corridor Assessment Survey method for the erosion sites. This method requires documentation of the length of the stream, the average height, as well as just some basic information on the severity of the erosion, the correctability, and the accessibility of the site. If you want to calculate the rate in which erosion is occurring on an annual basis, say, the bank erosion height index and near bank shear stress can be used to visually observe these different variables such as bank height, bank angle, root depth, surface protection, in order to compare these values against erosion curves from different regions, in order to translate into estimates of tons of sediment per year that would be eroding in a given area. Another way in which the function in which a stream is addressed is through channel evolution models. And there's a number of different conceptual models about the process by which streams change. You don't need to know the specifics of each of these steps, but having an idea of how streams change is important to provide some understanding of the relationship between land use changes or stream modifications and then erosion and sedimentation. So Simon and Hupp propose a 6-stage model in which channels modifications occur. So you have the pre-modified, step 1 you can see here, or class 1. The stream is stable with just mild aggradation, basal erosion on the outside bends, and deposition on the inside bends. In class 2, this is a channelized stream. So this stream has been channelized by straightening, by construction. So it's a trapezoidal shape with the vegetation removed. Here we can see in class 3, we have degradation. So banks are heightening and steepening. The flow line is lower to the relative to the top of the bank. Some pop-out failures of banks on the slopes may occur. Class 4, we see this is the threshold for degradation and widening. This is erosion down and out with large failures up the upper banks, and the flow line is very low in relation to the top bank. Slab erosion and pop-out failures will occur, and riparian vegetation is high and may lean into the stream channel. Class 5 is aggradation. So sediment begins to accumulate in the bottom of the channel while widening is still occurring. Vegetation is tilted or falling in at this form. And then in class 6, the old floodplain becomes a terrace and vegetation begins to grow in the new floodplain. So a new, smaller, bankful cross-sectional area is achieved with new stability. So conceptually, a stream will move through a series of stages until the stream reaches a new equilibrium. So knowing where a stream is in this process will help determine the BMPs. Associated with that model is the idea that the bank shape can help determine the channel's evolutionary stage. So for example, the gradual slope of a class 1 example shows that it's modified or a pre-modified channel. The steeper, longer slope in class 3 suggests that degradation has been occurring. And the added deposition at the base of the stream in class 5 tells us that degradation has occurred, but aggradation is now rebuilding some of the bank. The riparian zone has a lot of impact on the stream shape and the sediment transport. Even a small riparian zone can provide root structures to stabilize the banks or hold slumping banks together. Wider riparian zones provide additional benefits including water quality due to filtration, flood control by slowing down the waters entering the stream, and providing storage for floods, as well as habitat for wildlife. Much of this depends on the width of those benefits that are obtained. Based on literature review, the following widths are recommended to support various riparian zone benefits. For input, organic input through leaves and twigs and things like that, that can be anywhere from width for 10 to 30 feet. Water quality protection for a filtration barrier, that's going to be 16 to 100 feet. Stream stabilization through the root stabilization of the banks and moderation of the soil, that's going to be anywhere from 30 to 60 foot. So if you have a very small, you won't gain that benefit. Flood attenuation, so storing some of that flood water and intercepting overland sheet flow. That's going to be much wider, 65 to 500 feet. And then finally, riparian habitat, where organisms can live there, shrubs and trees to provide terrestrial wildlife as well as inputs for aquatic life. It's going to be 100 foot up to as big as you can get it. Now, the point that we need to circle back around to is that the fluvial geomorphology of the stream has a lot to do with the habitat present for aquatic organisms. So when we talk about different flow types, these also relate to different habitat types, left side versus right side of the screen there. The extent to which aquatic ecosystem benefits are provided by a stream depends on the presence and pattern of different stream structures. If a stream is unstable, some of the unique habitats may be buried or disrupted, or otherwise negatively affecting aquatic life. These will be addressed in more detail in the next session on a habitat assessment. So in summary, we hope that you've learned quite a bit about fluvial geomorphology. We hope that you've learned that it's the process where the water is transporting the wood and the sediment to create different bed forms and dynamic equilibrium. We hope that you've learned what happens when things get out of equilibrium and the effect that that has on the stream. And then we hope that you've learned some different ways in which hydrologists can measure this, whether they're measuring the transport of the sediment and debris, whether they're measuring the bed material itself, looking at channel erosion and stability, or how the stream is changing over time, as well as the riparian vegetation. This will give you a good platform to then understand the water quality benefits, the habitat, and then the biology that the hydrology, hydraulics, and geomorphology all support.